Today on Geographics, we've got another amazing script from Quentin Burns. So get ready to deploy your likes, give Quentin a shout out in the comments, subscribe to the channel and ring that bell if you like what we do here, and share this video with someone who loves learning about amazing places both in and out of this world. I'm Eric Malachite, your host for this episode, and let's get to it. You are standing on Mars at the shore of an empty ocean, waiting for the moon. You won't have long to wait. Phobos circles the planet every 7.5 hours, crossing the sky 3 times a day. It will rise in the west over the Amazonian plain and set in the east behind Olympus Mons. It will be shining and brilliant with distinct features, including a large bite taken out of the side. Phobos will appear smaller than Earth's moon. The bright star in the distance, its twin moon Deimos, is 10 times brighter than Venus shines upon Earth. These tiny bodies have occupied a huge space in human consciousness, making themselves anchors for myth, mystery, and conspiracy. Their origins and their substance remain unknown. Phobos was once said to be hollow, perhaps unnatural, the last remnants of an ancient Martian empire. When American astronomer Asaph Hall named the 2 moons in 1877, he didn't know he was creating a prophecy. Someday, Phobos will meet a spectacular doom. Someday, Deimos will be lost forever to space. To you, many of the stories are absurd, but you can't deny they have power. You are fascinated by the bite called Stickney Crater, the entrance to a spaceship you've heard. Soon there will be a mission to Phobos, and you may have your answers. You have a secret fear though. Will cold facts from the cold moon wipe the slate clear of myth? In Greek mythology, the twins Phobos and Deimos are fear personified. Deimos is dread, the sinking freeze before the battle. Phobos is terror, the red-hot panic when the battle is around you. They were the sons of Ares, the god of war, and Aphrodite, the goddess of love. As such, they also represented the fear that comes from love, the fear of loss. In some stories, Phobos and Deimos have a sister. Harmonia was the goddess of concord, she who ensured balance in the cosmos. Her descendants were cursed to suffer eternal tragedy by Hephaestus, the sculptor, god of stone and fire, as a punishment to her parents. The English naming of planets and moons was an accident that feels inevitable. Of course, they should be figures from myth, but they nearly weren't. The first 6 planets visible to the naked eye had been named many times before the Babylonians named them after gods. The Greeks associated them with similar gods in their own culture, and the Romans borrowed from the Greek associations. In medieval Europe, Latin was the language of science, so the Roman names endured. In the age of the telescope, it was up to the discoverers of planets to name them. The English astronomer who found the 7th planet called it Georgian Sidious, George's star, after the English king. No one outside England liked this, and other names were proposed and debated. Uranus, the father of Saturn, was the one that stuck because it favored convention. Nowadays, large features on Mars are given names from classical mythology. Features on Deimos are named for authors who wrote about Mars. Wait a minute, I wrote about Mars. When do I get a feature? Tell my publisher to get on that. Features on Phobos are split into 2 camps. Some are named for places from the novel Gulliver's Travels, which imagine 2 Martian moons over 1.5 centuries before their discovery. The moons are described as small and close to Mars, the near one with an orbit of 10 hours and the far with an orbit of 21. All impressively close to the truth. The other features on Phobos are named for scientists who made discoveries about the 2 moons. Our map of the Phobian landscape is therefore half speculative fiction and half revelatory fact. Phobos is a small, irregular space rock, 27 kilometers thick by 18 kilometers wide, a 3 to 5 hour walk in Earth's gravity depending on which way you go. Imagine yourself as Phobos' first cartographer, standing in the belly of the bite. Mars fills the sky above you. Its empty ocean, the Borealis Basin, is a vast dome across the heavens. It is thought to be the remnant of an ancient impact covering the northern 2/5 of Mars. The 10-kilometer Stickney crater is a tiny mirror of it, occupying half the surface of Phobos. As your feet sink into the thick dust of the moon, you feel the fear of myth made real. The gravity is weak, barely capable of holding you down. You have the weight of a hummingbird. If you jumped, you might fall into space forever. The crater you are in was named for mathematician, suffragette, and abolitionist Angeline Stickney. Stickney was Asaph Hall's wife, formerly his mathematics professor. She gave up her career when they married, but not her pursuit of science. Stickney was Hall's collaborator in the search for Phobos. He would have failed if not for her, but when she asked to be paid for her calculations, Hall refused. The cultural expectation of the time said an educated wife would serve as her husband's unpaid, uncredited assistant. After the incident, Stickney refused to do any more work on Hall's behalf. It is a smaller family drama than the one between Hephaestus and Harmonia, but no less damning, and both are equally recorded in the cosmos. When you climb out of the crater, you see a silent surface pockmarked by silent ages of meteor strikes. Assaults from space and Mars ground the rock into powder, carpeting everything in a fine calico of reds, grays, and browns. The regolith, the layer of loose dust and debris, might be 100 meters thick. Fine dust doesn't retain heat, so the dark side of Phobos is a bitterly cold -112 degrees Celsius. Here in the sun, it is -4, a chill winter's day. Long canyons stretch before you, disappearing around the horizon. From space, they were mysterious lines, dark trails running down the slopes of Stickney Crater to circumnavigate Phobos. Here, they are 30-meter deep trenches, origin unknown. Most of the trenches run in parallel, but some cross over each other. We got our first good look at the Phobian landscape in 1971, courtesy of NASA's Mariner 9 orbiter. In the late 70s, photos from NASA's Viking orbiters confirmed the difference between the twin moons. Phobos bore these strange marks and Deimos did not. The immediate suspect was the unknown architect of Stickney Crater. Long ago, something huge must have smashed into Phobos and deformed it. The trenches might be cracks from the impact, radiating outwards. This wouldn't seem to explain why some of them cross over each other, so perhaps there was a secondary culprit. The impact would have created an explosion of boulders, potentially a landslide. The boulders could have continued rolling around and around Phobos, crisscrossing their paths and cutting deep roads into the dust. Other moons in our system have similar craters, but no similar grooves. Perhaps it was something about Phobos' size and topography that made Stickney Crater different. However, upon closer inspection, the canyons were found to originate beside rather than within the crater. In 1945, American astronomer P.B. Sharpless found the first evidence of Asaph Hall's unwitting prophecy. Sharpless compared old data on Phobos with newer observations and calculated that in 60 years, the moon's orbital radius seemed to have shrunk by around 10 feet. We didn't know why it was happening or when the blow would fall, but if the data could be trusted, we knew what was inevitable. With a shrinking orbit, Phobos would eventually crash into the planet below, or else be pulled apart by Mars's gravity. 70 years later, a study by Terry Herford and colleagues at NASA's Goddard Space Flight Center on the canyons of Phobos noted that most of them begin on its Mars-facing side. They suggested the canyons are stretch marks caused by Mars's gravitational pull. The moon's gravity creates a tide in the land of Mars, a tiny bulge on the surface. We typically think of the tide as a force that moves water because water is easier to raise than land. In fact, the Earth and its moon deform a little as they pull against each other, but the deformation is so slight it can only be measured with precise instruments. Phobos is far smaller than Earth's moon and far closer to Mars. Gravity holds it around 6,000 kilometers from the surface, the nearest orbit of any moon in this solar system. As Phobos orbits, the tidal bulge circles Mars below it. Because the moon's orbit is faster than the Martian day, the bulge lags behind the moon. This lag acts as a tether, pulling Phobos back and gradually slowing its orbit. The tether is dragging the moon into Mars by 0.8 of an inch every year. The canyons are not scars from the past, but the first wounds of a long death. Herford's study answered the why. In another 2015 study, planetary scientist Benjamin A. Black and graduate student Tushar Mittal sought to answer when. They tried to predict Phobos' date of death by figuring out its Roche limit. The Roche limit is an invisible line around celestial bodies. A satellite held together by its own gravity can come so close, but no closer to the large body before the large body's gravity will tear it apart. Every satellite will have its own individual point of no return, depending upon the ratio of density between the larger body and the satellite. If the satellite is denser, it will last longer. If less dense, it will break apart sooner. If we know how close Phobos can come to Mars before tidal stress defeats its internal forces, we can estimate how long it has left. Black and Mittal looked at the factors in action, the tidal pull of Mars and the rotational forces on Phobos, acting to pull the rock apart versus the gravity and strength of Phobos itself acting to keep it together. Their calculations gave the moon anywhere from 20 to 40 million years. Previous studies gave it longer, up to 75 million years. The different results are down to different estimations of the density of Phobos, a long and strangely contested subject. In 1945, P.B. Sharpless had opened a mystery. In 1959, world-famous Soviet astronomer and astrophysicist Iosiv Shlovsky had a solution. Phobos must be hollow. Its orbit was too abnormal for any other explanation. Shlovsky tried. For Phobos to orbit Mars 3 times a day, it must be vastly lighter than expected for a body of its size. He was also struck by the moon's appearance. The surface reflected light strangely and looked too smooth and even to be natural rock. The suggestion, though radical, was obvious. Phobos was not natural. The smooth exterior was a metal shell, artificially constructed by unknown beings. We know that artificial satellites around Earth eventually come spiraling back down if left to degrade. Was this not the very thing we had observed happening to Phobos? American astronomer and planetary scientist Karl Sagan was captivated by the idea and struck up a correspondence with Shlovsky. Together, these two powerhouses of mid-century science writing popularized the idea of alien influence on human history. In the 1950s and 60s, aliens were all the rage. Dr. Fred Singer, the science advisor to American President Eisenhower, told the press that if Sharpless's data was correct, there was little alternative but to consider Phobos hollow, and therefore Martian-made. Stickney Crater might be an entrance, some people thought. And inside that entrance, Sagan and Shklovsky imagined an ancient society on Mars long since vanished. Some scientists, like the popular Soviet writer Felix Ziegel, expected to find still living Martians. 2 failed Soviet missions to Phobos heightened the mystery into a conspiracy. What was hiding within Phobos, and did it mean harm? Did the missions really fail due to technical errors, or were they attacked by something? Were the Soviets keeping the secret of aliens? Since the time of Shklovsky's calculations, we have learned a great deal more about Phobos. In the mid-2000s, the European Space Agency's Mars Express orbiter began gathering better evidence of the moon's composition. The density was estimated at around 1.9 grams per cubic centimeter. Phobos is probably porous, with large empty spaces within it, but not fully hollow. Better photos showed that the smooth surface is certainly made of dust, not metal. In these photos, Phobos looks similar to C-type asteroids, loosely bound masses of blackish, carbon-rich rock. These asteroids formed in oxygen-rich regions of the early solar system and are typically 10% ice. Assuming a similar composition to C-type asteroids, Black and Mittal sought to estimate the moon's strength using a geotechnical model designed to simulate the behavior of rock and soil in large underground construction projects. From this, they predicted that Phobos' Roche limit will be 3,400 miles from the surface of Mars. Once it crosses that line, Phobos will be hastily stripped of its vêtements, layers of dust and rock flung into orbit. Within a week, Mars will gather up a dark ring, thin and dusty like Jupiter's. In time, the ring will disperse. According to Black and Mittal, it might take 1 million years or 100 million, but no longer. In the cosmological timescale, the afterlife of Phobos will be fleeting. Phobos' death is known. but its birth remains a mystery. Because of its irregular shape and carbonaceous composition, Phobos was long thought to be an asteroid that strayed too close to Mars and was captured by its gravity. There is a problem with this theory. Phobos has a nearly circular orbit around Mars's equator. Computer simulations of the capture of an asteroid predict irregular orbits, which are typical of asteroid moons. Most moons in this solar system began life as disks of rock and dust around their planets which gradually coalesced. Perhaps Phobos was one of them, but in that case it becomes difficult to account for Deimos. The two moons are so far apart that to form them a massive disk would have been needed. Such a disk would be much likelier to collect itself into a single huge moon. There is also the question of timing. If this disk was present in Mars's history, its formation and dispersal would need to match the ages of Phobos and Deimos. The impact that created Borealis Basin on Mars would have created a large enough rubble disk to form moons. We don't know when the impact happened, but the crater is thought to be extremely ancient, from the earliest age of the solar system. Most of our system's moons formed then, in the time of chaos and battle. Leftover materials of creation were everywhere, and giant impacts were common. A disk that old could not have formed Phobos, though. Given its orbit, it would have long since passed its Roche limit. Planetary scientist Amir Hassan Bagheri suggests that, although Phobos is much younger than Borealis Basin, it might still be made of it. In a study with the Swiss Federal Institute, Bagheri and colleagues proposed that Phobos and Deimos could be the remnants of an older, larger moon, born from the rock of Borealis Basin and shattered later by another huge impact. They analyzed the latest data on Phobos and Deimos and found that the orbits of the two moons might have intersected somewhere between 1 billion and 2.7 billion years ago. When that first unknown moon was destroyed, debris would have pummeled Mars. Many of the craters on Mars are around that old. It seems possible that the hammer of Hephaestus fell upon Harmonia, blotting her from memory and cursing her descendants to misery and doom. In 2015, the Japanese Aerospace Exploration Agency announced plans for a mission to Phobos. The Martian Moons Exploration, or MMX, will launch in 2026 and enter Martian orbit in 2027. From orbit, the 4,000-kilogram spacecraft will send a four-legged rover called Iosiv to land on the surface of Phobos. It must choose its landing spot carefully and land very gently, since the moon's gravity is too weak to keep it from bouncing off again. MMX's landing gear is robust, and every stage of the mission is being carefully planned and replanned. On Phobos, Iosiv will drill a few centimeters into the regolith and gather a sample. The return module should drop out of the sky above South Australia in 2031, whereupon it will become the first ever soil from the Mars system to return to Earth. One goal of the mission is to uncover the truth of Phobos' birth. If the materials from the samples match materials analyzed on Mars by orbiters, landers, and rovers, it could confirm a Martian origin for Phobos. Sonia Fornacier, instrument scientist for the mission and astronomy professor at Paris Site University, anticipates otherwise. Fornacier was using images from the European Space Agency's Mars Express spacecraft to adjust MMX's route to Phobos when she discovered a trove of 300 unpublished photos. She led a new study of Phobos based on the photos and wound up with a third possible origin story. One cannot directly analyze the chemical composition of rock from photos of the rock. What we can do is analyze the properties shown in the photos and compare them to properties of rocks we know about. Fornacier's study looked at light and reflection. In photos where the sun was directly overhead, the sunlight that reflected off Phobos was bright and intense. When the sun was at an angle, Phobos was less bright, and the surface appeared porous and sandy. Phobos doesn't reflect uniformly. Fornacier's team suggested its dust carpet is made of grooved particles, whose myriad tiny shadows disappear in direct sunlight. Then they asked, what else reflects this way? They found that the properties shown in the new photos are shared most closely with Jupiter family comets, comets with orbital periods of under 20 years. Comets and asteroids are remnants of the birth of the solar system. Asteroids are rocky and most reside in a belt between Jupiter and Mars. Comets are small balls of dust and ice that live out beyond Neptune. Sometimes they draw too near Jupiter, who pulls them in and changes their orbit. When they visit the inner solar system, their ice turns directly to gas, forming their classic tails. If Phobos was not a captured asteroid, but a captured comet, it would be the first known comet moon in our solar system. Of the 7 comets that have ever been imaged in high resolution, 5 were found to be bilobed, meaning they have 2 heads connected by a thinner neck. Sometimes, when they fly too close to the Sun or to Jupiter, gravity increases their spin and they split. The 2 heads orbit each other for a time before gradually rejoining. Phobos and Deimos may have once been a bilobed comet. This 2-as-1 body could have joined Mars as a single moon, before eventually being pulled asunder by Mars's gravity. Perhaps the moons of Mars are 2 halves of a whole, keeping watch on each other but never to be reunited. While Phobos draws towards Mars, Deimos drifts away. Someday its orbit will be wide enough to escape the planet's gravity, and it will venture once more into space. Someday, the twins will be parted forever. This theory, like the others, is uncertain. The quality of light measured on Phobos and the light measured on Jupiter family comets don't match exactly. Fornasier's team is running simulations to determine the likelihood of Mars entrapping a comet. In 2031, we may know the answer. Discovering the birth of Phobos is one goal of MMX. There is another goal. This mission is our best upcoming chance to finally answer the question of life on Mars. But why go to Phobos and not Mars itself? Phobos has been brutalized by Martian debris for millennia. We know impacts between celestial bodies can send material across the solar system. 3% of meteorites recovered on Earth were found to be from Mars. Phobos, being the closest body to Mars, will have vastly more of them. Numerical simulations suggest that the swimming pool-thick layer of dust has over 1 million tons of Martian material mixed in. A sample return mission to Phobos is much simpler to execute than a sample return from Mars. The low gravity will make it easy for the rover to escape the surface, and the low mass should make for a loosely bound regolith and easy to collect samples. Mars is a huge place to search for evidence of life, and if that evidence exists, billions of years have obscured it. Phobos is tiny and should provide a randomized grab bag of materials from different regions and eras of Mars. When they analyze the material, the MMX team will be searching for shigai, sterilized and harshly irradiated genes and ancient imprints, or dead remains in Japanese. Life may leave behind structures and molecules it made, and even echoes of its preferences. The life we know favors isotopes with fewer neutrons, choosing carbon-12 over carbon-14, for example, thereby changing the chemistry of the rock record. From a dusty grave thousands of kilometers from home, the whims of ancient life may still be known. In 1966, Iosiv, Shlovsky, and Karl Sagan released Intelligent Life in the Universe. It was Sagan's first major book. It was written in an unusual style. Shlovsky's portion had been published in Russian several years earlier. Sagan added elaborations, figures, and literary departures in his own voice, demarcated with a symbol. Sometimes Sagan and Shlovsky switch back and forth within the same sentence. The book speaks with 2 voices as one, another kind of 2-as-1 body. The authors were never able to meet, but from opposite sides of the globe they exerted a powerful pull on each other, and on the tides of human culture. Some would say, for the worse. In the book, Shlovsky and Sagan postulate that aliens might have visited the Earth and influenced early human history. They suggest that myths and religion should be plumbed for evidence, noting that the Sumerian gods were of celestial origin. Undeniably, there is a connection in human culture between mythology and space. Ancient astronaut theories suggest one way of mapping the connection, by looking inwards as a way of looking outwards, but perhaps they have it the wrong way around, and more than likely they do. As the nuclear arms race intensified, Sagan became worried about humanity's future. The more advanced our civilization became, the closer it danced to self-destruction. Suppose we learned the trick of launching huge satellites, marvels of modernity, and then one day those satellites were all that remained of us. Silent, brilliant monuments that might one day be found by some distant species, searching the galaxy for hints that they too were not alone. Our satellites would need to be found before they crashed into Earth, and all trace of us was lost forever. That urgency is written into Sagan's response to Phobos, for if such a tale could be told of Phobos, then we had found the Martian monument just in time. Hope, too, is written there. The death of one's planet's civilization does not mean the end of intelligent life in the universe. The quest will go on, even if not by us. What is that quest? What is it that we are seeking in space and from Phobos? We want to know the truth, and we want to know the story. We want science and myth together. They drive each other. The map we make must reveal both Gulliver's fancy and Angeline Stickney's reality. The birth and death of the twins Phobos and Deimos, and the forgotten curse of Harmonia, must be told in full, in all speculative and scientific glory. Dead remains in the dust must be allowed to speak. Worry not that fact will obscure myth, for they are bound together. Seek truth and tell the story. Science needs to get better at telling stories, telling its story, because what we find in pseudoscience is that people are attracted to the story of aliens seeding human civilization, even if there's no substance there. They're less attracted to the boring facts or what have you, even though those facts are far more interesting when you put them in context. How you frame that story is really important. And science communicators, like myself, like Neil deGrasse Tyson, like Kyle Hill, will have to learn how to tell those stories more effectively and make them just as powerful as myths. At least that's how I'm interpreting it. I hope you learned something today, and if you like this video, be sure to deploy your likes, comment your favorite thing about Mars and Phobos, subscribe to the channel, and ring that bell if you haven't, and share this video with someone who loves learning about out-of-this-world places. See what I did there? I'm Eric Malachite, and we'll see you next time.